Hello, Earth Science students. This is Dr. Lowe again. So I'm recording the week 3 lecture where we will be talking about light, the sun, and beyond the Milky Way. This lecture is actually fairly short. The chapters, I don't go into as much detail as the chapters do. At the end of this lecture, I am going to be going over a little bit of test taking 101. So some ideas about how to study, um, how to actually take the test, strategies, things to watch out for. And remember, exam 1 is going to be next week in week 4. It actually works out better with the topic material for it to be Monday, Tuesday, but I will discuss that with the classes on during week 3 to make sure we get the schedule set up. And I will talk a little bit during actual class about the format. So let's get right into it. The universe. This textbook, the very, very, very last thing covered in the textbook is how the universe is formed. I've already discussed it a little bit because I think it's important to talk about how things start before we get into the way things are. The textbook apparently has a different opinion on that. So cosmology is the study of the universe in general. There's a lot of stuff to study with the universe. So the universe started with the Big Bang, which was about 13.8 billion years ago. So that is the beginning of everything. And the Big Bang is this idea of suddenly there was stuff. There was nothing and then there was stuff. And the Big Bang was extremely hot. Once material cooled enough, subatomic particles combined to form our first elements, which were the numbers 1 and 2 on the periodic table, so hydrogen and helium, primarily hydrogen. Gravity then condensed the gas into clumps, and eventually those clumps became stars, and then eventually those stars combined to be or joined up into orbits to become galaxies. The first stars were formed about 200 million years after the Big Bang, which is very short when we're considering the Big Bang is 13.8 billion years ago. Those early stars were primarily hydrogen. They were very, very massive and they had a very short lifespan. Because of this, they died very explosively. And the deaths of these early stars is what led to the formation of newer stars, and this is where we were able to generate more of the complex elements. So as we have more explosive deaths and combinations, we can only form elements up to a certain complexity within a regular star. We have to have some of these larger stars exploding in order to form the more complex elements. So it was through these early star deaths that we were able to actually completely form our universe. Sorry if you just heard Heidi shaking her ears. Luckily, she does not have her collar on right now because she just had a bath, so she wasn't jingling when she did that. The universe is also expanding. We see much evidence. All evidence that we see shows that galaxies outside our local clusters are all moving away. We see that everything seems to be moving away from us. The further galaxies move away more, we can think about this as this idea if we have bread dough that has objects in it like raisins, and we let that bread dough rise as it does from the yeast, the raisins will, as the bread is expanding, the raisins will also expand from each other, and they will expand at the same rate, basically, that the bread is expanding. So if the bread doubles in size, the distance between the raisins will also double in size. So that means that raisins that started off further apart get even more far apart. And we call that Hubble's law, that galaxies recede at speeds proportional to their distance from the observer. So the further away a galaxy is, the further it gets away. This expansion of the universe should produce cosmic microwave background radiation. This was theorized, and it was found in 1965 that we are seeing this. So all evidence says, yes, the universe is expanding, which is a hard thing to get your mind around it because the universe is everything that is, but it's also expanding. So it's everything that is and everything that will be because it's getting bigger constantly. So what happens if, the universe is expanding? Okay, we had the Big Bang at the beginning. What's going to be at the end? Which is not something any of us have to worry about. So the universe is expanding, but can it continue to do so? Is it going to keep expanding forever? It can't keep expanding for absolute ever. So there are two ideas. One is the big chill, which is this. Well, okay, there are more than two ideas. There are two major ideas that are covered in your textbook. So those are the only two I'm going to address. So the big chill is this idea that the universe will continue to expand until stars burn out and it'll run out of energy, and then it will have a gravitational collapse. Or I'm sorry, um, it will um, continue expanding until we run out of energy, um, and then all the stars burn out, and then it just dies. That there's nothingness. Um, the next one is called the Big Crunch, and that is that expansion will slow down, so it won't continue to expand. Eventually, that expansion will totally cease, and because we don't have forces acting against gravity, gravity will start to pull everything together and it will crunch down together, and then it will basically collapse down into one giant black hole. The thing that's going to determine which one of these happens is density. So if we're greater than the critical density, gravity should prevent continued outward expansion. So if we're beyond that critical density, we should be balanced between gravity and expansion. So what is actually happening? Well, we just said a second ago that the universe is continuously expanding. So obviously gravity isn't fully, we're not at that point. Gravity's not preventing outward expansion. So we have two explanations for observations. So we have dark matter. So has been proposed because we observe that all stars orbit galaxy centers at a similar speed, regardless of size and really distance. Um, we need a way to explain this. They shouldn't all be orbiting at around the same speed of their galaxy center. There should be variation. The explanation for that is a thing called dark matter. So this is missing matter that explains the variations in, or the fact that we have no variation really in orbital speed of stars around galaxies. The other most important one for what's going to happen to the universe is this idea of dark energy. So dark energy is what we use to explain the fact that gravity should be slowing down expansion, but expansion is speeding up. We see that the universe keeps expanding. So something out there is speeding up the expansion that's counteracting the gravity, and that is dark energy. Of these two, dark matter and dark energy appears to be the stronger. So it's thought currently that the big chill is the more likely outcome of the end of the universe, that we're likely to continue expanding until we, burn out all of our stars. Again, not something any of us has to worry about. How do we observe space? Well, we use telescopes. Telescopes are actually fairly old technology. Your textbook goes through some of the early telescopes. The earliest telescopes were optical, and we still use optical telescopes. Optical means that we're bringing an image to an eye or a computer. The earliest ones were what are known as refracting telescopes. That's this upper image here. So refracting telescopes bend light to focus it, to bring it into sharper image to our eye. It's what happens with eyeglass lenses. That is what you're doing with a pair of eyeglasses, that you are sharpening the image. A telescope is just doing it from further away. They have a limited distance that they can see. It's going to be dependent on the lens, and the size of the lens as well as the length of the tube. So if you make this lens bigger and you make this tube longer, you're able to bring in further light to focus it. But there is a limitation on how big you can make these things. The more updated technology in optical telescopes are called reflecting telescopes. Reflecting telescopes is the second one, this bottom one. They use mirrors and they bounce light to focus it. So you will bounce light Light comes in, it bounces off a primary mirror, it hits a secondary mirror, and that's where it's going to focus to your eye. The benefit of these is that you can focus further light in a shorter tube. You don't have to have nearly as long of a tube. Um, you can also, depending on the shape of this mirror, you can make these much bigger. Again, still limited on how big you can make these, but this is a vast improvement over the refracting telescopes. The other thing we can do with reflecting telescopes is we no longer need to have a single mirror. We can actually make a large mirror that is in sections, and we can change the shape of the mirror with those sections. It's much easier to modify mirrors than it is the transparent lenses that we use in refracting telescopes. So that leads into the modifications that we have of telescopes. We can have what are called active and adaptive optics. So this is the idea that we will actually change the shape of the mirror. And we can do this for different purposes. The main purpose is going to be that we can modify the mirror to adjust for interference in the transmission of the light. So for example, we can adapt the shape of the mirror in order to account for some of the interference that the light will encounter in our atmosphere. And so we can make a clearer transmission. In addition to looking at information from space with our eyes, which is what optical telescopes would be, we can also listen to space, and these are called radio telescopes. So radio telescopes listen for energy that's outside the visible spectrum, which I will discuss in a second. But basically, light in the visible light is a very small portion of the energy of the universe. We see that here. The rainbow here is visible light. So some of our telescopes can look beyond this visible spectrum, but you can see that there's a significant amount of energy outside that visible that visible part of the energy spectrum. Radio waves are very long frequency. They are very low energy. So we can listen to this energy in this part of our spectrum, which again I'll talk about in a second. Radio telescopes have to be very large because they are trying to catch this very broad energy. So they tend to be Earth-based because they're very big. Here's a radio telescope. They are large. So they are not going to be space-based typically because it would be very difficult to have one of these, send one of these up into orbit. We do send telescopes to orbit. So we have telescopes that will be optical, that they're taking images. We have ones that are looking at other parts of the electromagnetic spectra. And space-based telescopes are probably the newest type of telescopes we have. They are very useful because they remove any sort of impact from our atmosphere. So this image is showing us that our atmosphere does block much of the energy from reaching the surface. So one of the things that we do with our observatories or telescopes is we tend to put them at high elevations, preferably in places that have fairly clear weather. So there's an observatory, for example, on Mauna Loa, because it's at a high elevation and it tends to have fairly clear weather. We also have telescopes that are in Chile that are up on the plateaus. We do this because they are in less atmosphere, so they have less interference, and then also that we can try to have less cloud interference. That sometimes we can actually be above certain layers of the clouds. But we still, anything on Earth-based is going to have an impact of the atmosphere. But if we can send the instrument outside the atmosphere, well, then we no longer have to worry about those impacts. So, it's not just impacts, but the atmosphere, by its very nature, intercepts much of the EM spectrum. So much of the information is actually trapped or repelled by the atmosphere. We also can remove sun interference with these space-based instruments, so that we don't have the sun's impacts. Space-based instruments, by their nature, can only be a certain size, though, because we can only send such sized things into orbit. The bigger they are, the more difficult it is to send to orbit. They're also more difficult to maintain. Hubble, for example, had issues that it wasn't bringing back or sending back clear images for a long time because it had broken hardware. And it's difficult to fix these because you have to have a mission that goes to space to fix the instrument. So benefits, yes, but also drawbacks. This is true of any type of scientific instrument. The final way that we can put telescopes together is we can actually use multiple telescopes to make them stronger. So we call these arrays. So we'll take several instruments and use them in conjunction so they act as a larger instrument. So sometimes it's just two instruments. For example, the observatories in Chile, they have twin instruments that work together to be stronger. This is very frequently done with the radio telescopes. That you might have a like an X or a cross design to them, and it makes them able to observe further and more clearly. So what are we observing? With optical, at least, we are observing light. So light is a very, very small portion of what's called the electromagnetic spectrum or electromagnetic radiation, shortened to EM often. So the EM spectrum, and it's called a spectrum because we go from very, very high energy to very low energy, and we go all the way in between, so we call this a spectrum. So the highest energy are called gamma rays. We think about this energy as either waves or particles. So we think about it as a wave, that it is this undulation up and down of energy. The closer together the tops of those undulations are, so the top of the wave, the peak of the wave, the closer together they are, the higher the energy. So the shorter the wavelength is the distance between these peaks. So the distance here. The shorter that is, the higher the energy. So gamma rays are our highest energy, our shortest wavelength, EM. So gamma rays are 10 to the negative 12. So that means that we're moving the decimal place at the end of this 10, 12 places this way. 12, by the way, is trillion. Whereas radio wavelengths can be, 10 to the 2, which would be 100. And this is in meters. X-rays, so X-rays being the things that we use to image the inside of our bodies, they are 10 to the negative 10. So this is like nanometers, basically, or hundreds of nanometers. So this is the amount of, this is why when you take an X-ray, they try to protect the rest of your body from the X-rays because they are very high energy and you don't want to expose unnecessary tissues to that high energy. Then we have ultraviolet light. Ultraviolet light is higher energy than visible light. UV, you may have heard, is ultraviolet. So this is the type of radiation we're worried about for damage from the sun. So sunburns are due to ultraviolet light. So we want to try to block as much of that from impacting us as possible. Then we have visible light, which is a very short spectrum. The different colors that we see are going to be due to different wavelengths. So the highest energy is going to be violet, which is right next to ultraviolet. Um, so if you know the term Roy G. Biv, it's actually goes from lowest energy to highest energy. So red, orange, yellow, green, blue, violet. I'm sorry, I missed indigo. Red, orange, yellow, green, blue, indigo, violet is the order from lowest energy to highest energy. And those have different wavelengths. So we are actually, when we're seeing those different colors, we're actually seeing objects vibrate at different frequencies, different energies. Infrared will be on the far side of that. So it's longer wavelength, lower energy. Red is the longest wavelength of visible light. So infrared is on the next side. Infrared is heat. So infrared's also used in like lasers. But yeah, infrared is going to be heat being radiated. And then the longest wavelengths, then we have microwaves are between infrared and radio waves, and then radio waves will be the longest wavelengths. So the inverse of wavelength, so 1 over wavelength would be frequency. I'm sorry, I said that wrong. The inverse of period. So we can think about wavelength as being the distance between peak to peak. We can also measure that in time, and the time would be called the period. So the number of seconds it takes for this peak, the spot that this peak was at, to then have the next peak would be considered the period. If we do 1 over the period, that's called the frequency. So the number of peaks that go through a spot in 1 second is the frequency. And we measure that in hertz. Hertz is per second. In radio waves, they give a radio stations give a number. You have 105.7 is the point. 106.5 is the arch. Those numbers aren't just arbitrary numbers. Those are actually the frequency that those radio stations are transmitting their radio waves. So that's the frequency, which is the inverse of period, and period is related to wavelength. But you can use that to figure out how far apart the radio wave signals are. At least that's for the transmitted radio waves. Now that we have like digital radio, it's a little bit different. But there's a reason why they had those numbers. And on old-fashioned radios, you would actually move your dial and you could hear, as you moved your dial, you would hear the radios start to come in, or the radio stations start to come in, and then they would get strongest when you hit the proper frequency. But you started hearing it as you approached that frequency. Those frequencies are used in other cities as well. So, oddly enough, where I lived in Philly, several of the radio stations had the exact same numbers. So I had my radio programmed in my car, and I didn't always have to, I had a set for each city, but there were a couple of radio stations that I was reusing the same numbers between the cities. So it got confusing when I was like, am I on my St. Louis set or my Philly set? Because both of them have a 98.1, and I'm not sure which one's which. But yeah, that's why the call numbers are what they are. So waves and particles. So you can think about energy as being this wave. It's often thought of in this idea of a wave of energy. And so that's where we're going to have the wavelength, which is the space between the peaks, and frequency is the number of peaks that go through one spot in a certain amount of time. So it's a measure of how fast the peaks are moving through. So you can imagine that if you have a shorter wavelength, you're going to have higher frequency and higher energy, therefore. Longer wavelength, you're going to have lower frequency and lower energy. We can also think about energy, this EM spectrum, as being particles, and these would be photons. So this is if we think about that we're actually going to have a ray of energy coming out, and we call these photons. They exert radiation pressure. So this is where, we had the idea of comets, that we had those tails were being pushed back by the sunlight. This is how we do that. We call the EM spectrum. So spectrum is singular, spectra would be plural. There are different ways to look at the spectrum. So we can have it be, think about the continuous spectrum. So this is the idea of that we are going to split the spectrum into a continuous array of colors that visible light would split in to everything from the Roy G. Biv. So this would be the continuous spectrum being demonstrated. We can also have what's called an emission line spectrum. So this is the idea that we have an energy source and it's going to go through a prism, or it's going to come into an instrument, and instead of seeing the entire spectrum, we are only going to see certain bands that are going to be specific to certain wavelengths. And so we'll see either certain colors, or those certain wavelengths will be corresponding to specific elements. So when we have these emission line spectra, or if we have absorption line spectra, which will be the opposite. So absorption line spectra is when we have the energy is passing through our prism or our instrument, and we see areas where we're not seeing energy, that we have this dark line, and we have the continuous spectrum except we're having gaps. When you have either emission that we're allowing it through, or absorption where we're not allowing it through, these are going to be at specific frequencies, and we can use that to determine elements. So we can use these type of spectra, this emission and absorption, to determine what elements are present in a star, for example. And that's very, very useful for planetary studies. So we can learn quite a bit from light. So I already mentioned spectra, and so this would be an example of that absorption spectra that we see. Different, that calcium has absorption lines in the violet, blue range. Iron has one here that's around like 475-ish maybe, and then it's got another one that's at like 525. So these different lines combined together will tell us what elements are present from a light source. We can also look at the speed of light. So the speed of light in a vacuum is 3 times 10 to the 8th meters per second. If light gets slowed down for some reason, that tells us that it's moved through something. Also, the fact that it takes this time, what we're seeing is actually past stars. So when we look up at the night sky, we are seeing stars. Some of them are no longer alive. Some of them are dead stars. Very, very distant stars. It takes us a long time for light to reach us. Remember, we measure the distance between distant objects in the solar system in light years. So it's the number of years it takes light to travel. So if things are hundreds of light years away, well, we're seeing hundreds of years ago when we look at those stars. We also can see the composition. So all materials will have distinct frequencies, and the way those combine, we can determine what elements are present. We can also look at temperature. So hotter objects will radiate more total energy per unit area than colder objects, which seems a little bit obvious that hot things are going to have more energy than cold things. But the color will also indicate the temperature. So blue is going to be hotter than red. It has more energy. So blue-white stars are hotter than red stars. And that's what we're seeing here. That, our sun is a yellow star, which is kind of middle of the road. On a side note, I was looking at light bulbs earlier today, so I'm going to say it. If you ever have wondered why the heck they give you the color of the light in this thousands of K or hundreds of K, this is what they're giving you is the temperature. So blue white light is going to be hotter than yellow light. Um, so that's what, if you've ever read the back of a light bulb where they give it in lumens, they also now give it in, you know, you'll see things that might be something that looks like this, where it's a large number and then it's K, and so you might see 6,000, you might see 8,000. I can't remember off the top of my head what the light bulbs I was looking at were saying. That is indicating the color of the light, and it's based on the temperature, how hot the light is burning. And you will see, daylight versus soft white will have a different rating on them. And so they will have a different type of, will it be bright white or will it be more of a soft white? And it depends on, is it, the higher the number, the more bright white it's going to be, the lower the number, the more gentle it's going to be, I guess. The final thing that we can get from this light, or one of the final things we can get, is a very important concept, and it's the idea of motion. So we can tell if objects are moving away from us or towards us. So if we look at our standard absorption lines for a element, and we observe from the star we're observing that those lines are moved from their standard location. So this first panel is showing us the standard sodium lines, and that would be this section here. So this is what sodium should look like. If our observed lines are actually further into the red, we call that red shifted. It's shifted into the red. If they are further into the green for sodium, which started off in the yellow, they're more towards the blue, we call that blue shifted. This will tell us if the objects are moving closer to us or moving away from us. So if they're moving away from us, they will move into the red. If they're moving towards us, they will move into the blue. What's happening is the Doppler effect. So as objects move closer to you, the energy will start to stack up and start shortening their wavelength and becoming higher energy, and they will then move towards the higher energy state, which is the blue. So they will be blue shifted. As objects are moving away from us, the energy will become more spread out, which will become longer wavelength, which will then move towards the longer wavelength, lower energy state, which is red. So this is the Doppler effect. We see this if we are standing and listening to an ambulance move towards us. As it's moving towards us, it becomes higher frequency. The sound changes. It's because those sound waves are stacking up on themselves and becoming higher energy. As it's moving away from us, it becomes lower frequency because it is the energy is being spread out, so it's moving to a longer wavelength, a lower energy state, and so it's lower frequency. The same thing happens with light. So that's why that objects that are moving away from us are called red shifted, because they're moving to the red wavelengths, which are lower energy. Okay, it's not necessarily moving into the actual red, it's moving towards the red. So for example, if we look at some of these like hydrogen lines, they're never going to get, well, that one would. Let's look at calcium. Calcium's all over here in the violet. So calcium would never get all the way over to the red, but would move towards the red. And we call them blue shifted if they're moving closer to us because they're moving towards the blue. Why it's blue and not violet, I'm not sure, but it's called a blue shift. We see more red shifts than blue shifts because things are mostly moving away from us. Very few objects are moving closer to us because remember, everything's expanding. So what about our closest source of light? That would be our star. Our star is a middle of the range star. Middle of the range age, it is middle of the range temperature, it's a yellow star. Middle of the range energy, everything's middle of the range. It is in what's called the main sequence, which I'll talk about in a second. Our star does have layers, like all the other objects in our solar system. It has a core. There is then outside that core a radiation zone where we have energy moving outwards. Um, Beyond that radiation zone, we have a convection zone where we have movement of material in convective cycles. So we are circulating material within that convective zone. These are all very big areas, I will add. Remember, the sun is very massive. We then have a photosphere, which is the visible surface of the sun. It's about 500 kilometers thick, so it's very thin, um, and it's not smooth. So the sun may, don't look at the sun, but images of the sun, at least from a distance, make it appear very smooth. It's not. It's very granulated. It has granules because it's gas that's um, being held in by gravity. Outside the visible surface, the photosphere has a chromosphere. The chromosphere is basically the sun's atmosphere. Um, the chromosphere is several kilometers thick, or I'm sorry, several thousand kilometers thick. It is what causes the gases to eject out periodically. Then we have outside, we have the corona, which is the emitted light that we see coming out. So in a star, we have energy. The energy is due to nuclear fusion. I will add, your textbook goes into a lot more detail in the different layers. If it's your thing, go for it. The important thing to me is what the sun does for our planet. The sun provides all the energy for our solar system. So within the sun, we have energy through nuclear fusion. So we have proton-proton chain, that we're having two protons combining. That will turn, or we have multiple protons combining, I might add. That reaction will take 4 hydrogen that each have 1 proton. So a hydrogen has just a proton. That is what hydrogen is. So those 4 hydrogen protons will turn into 1 helium atom, which is 2 protons and 2 neutrons. And then there will be some leftover energy. So E equals mc squared. E is energy equals mass times E equals mc squared, mass times the speed of light squared. I wanted to double check the c was the speed of light and not another constant. So it's energy is going to be equal to mass times 3 times 10 to the 8th meters per second squared. So you can imagine that your energy is rather big because the speed of light is, again, 3 times 10 to the 8th meters per second. You square that, and that gets to be a pretty big number. If we look at helium, it is only 99.3% of the mass of those 4 hydrogens. So we have lost, 0.7% of the mass of those hydrogens. This means about 600 million tons of hydrogen converts to only 596 million tons of helium. So there are 4 million tons of matter converted to energy every second within our sun. 4 million tons of matter is being converted to energy. And we look at this where energy is going to be that matter times the speed of light squared every second. Our sun is a energy producing machine. So we produce significant amounts of energy constantly. There's a reason why it is powering the entire solar system. The sun has some interesting features. So we have dark blotches on the sun. These are called sunspots. They oftentimes will happen in a pair with smaller sunspots around them. So that's what we see here. We have 2 main sunspots, and then we have some smaller ones around them. The black center of the sunspot is called the umbra. The lighter region outside it is the penumbra. These are only actually dark in contrast to the rest of the sun. If we were able to isolate this, it would be extremely bright. It's just that compared to the extreme brightness of the rest of the sun, they appear dark. They are going to be governed by the magnetic field. So the magnetic field of the sun, which again, we have convective layers of gas within the sun. So the magnetic field of the sun is pretty strong. The magnetic field will connect pairs of sunspots. So we see that happening here, that we have magnetic lines will connect the sunspot pairs. We actually can, this is an image of the magnetic field, and we can see these connections on the sunspots from the sun. The field is 1,000 times stronger in the sunspot than the surrounding region. So we're focusing the magnetic field into these regions. So we can actually have changes in solar activity due to increased sunspot activity because we're changing the magnetic field of the sunspot. These sunspots actually will be cooler than the rest of the sun because the magnetic field is going to disrupt the convective flow below the sunspots, so they will be cooler, which is why they appear darker because they have less energy. They're cooler. We can also have changes in the amount of solar radiation coming out during intense air times of sunspots because we are altering the magnetic field within the sun and also altering the surface temperature if we have intense sunspot activity. We can also have solar features that will leave the sun. So these are prominences, solar flares, and coronal mass ejections. Prominences are a cloud-like structure of chromospheric gases. So this is basically clouds around the sun. They are quiescent prominences if they hang motionless around the sun. If they leave the sun, we call them eruptive prominences. So they explode away from the sun. So if the gases shoot out from the sun, they're eruptive. If they're just kind of hanging around the sun, so like these ones would be quiescent prominences. A coronal mass ejection is where we have a eruptive prominence that's completely left the sun, or it could be another type of storm. So that's what we're seeing here, that they've completely left the sun's surface. They're no longer caught within the gravity. We can have a solar flare, so that would be a brief outburst we see it as a sudden brightening, and it tends to occur above a sunspot cluster. So we have an outburst of gases above a sunspot. And then when we get these things that actually leave the surface of the sun and they interact with our atmosphere, those are called auroras. So we see a glow in the Earth's upper atmosphere due to these coronal mass ejections. It is the aurora borealis in the North Pole. Borealis refers to northern hemisphere. It's the aurora australis. I always try to add another alias in there. Australis in the southern hemisphere. It's a abbreviation of Australia. Aurora australis. If you ever heard the term austral summer, that refers to the southern hemispheres, that we have the boreal northern winter at the same time as the austral southern summer. We'll talk more about seasons later on in the term when we talk about weather. When we look at stars, we always like to classify things. A theme throughout this class, is we will want to assign values to things. We want to put things on rankings. The way we do this with stars is we look at the luminosity, the brightness. This is also called absolute magnitude. So it's, how bright is the star? Sorry, my throat got dry. There are different ways to look at how bright a star is, though. So one we call apparent magnitude. Magnitude being the measure. We call it apparent because it's how bright the star appears from Earth. On both of the scales for brightness, we will have positive numbers be less bright, lower numbers or negative values are brighter. So if we look at this chart, the negative numbers are towards the top. These are the brighter stars. The positive numbers are towards the bottom. So the smaller the number, the brighter things are. The bigger the number, the less bright things are. I said that wrong. That's for magnitude. Luminosity is the opposite. Luminosity does have the bigger the number, the brighter the star is. So it's just for the actual, if you are looking at the magnitudes are measured with these negative numbers being bigger, positive numbers being smaller brightness. Absolute magnitude is how bright a star truly is. So again, the lower the values, the brighter they are. Excuse me, the brighter they are. This is measured as being a standard distance of 32.6 light years from, as an observation point. So basically, we're going to say that we're going to look at all the stars from the same distance and then compare how bright they are. And that will give us a actual measure of the brightness. Because you can think about it, if we're looking at the apparent magnitude, a star that's really, really far away and really bright isn't going to appear as bright as a star that's closer, but maybe not quite as bright. So that's why we have to look at this absolute brightness that will tell us, we're looking at the exact same measure of the value of the light for all the stars. Again, luminosity is a measure of brightness as well. It is comparable to absolute magnitude, but it does go from very small numbers for the less bright to very big numbers for the very bright stars. We can also look at color. A color is going to be an indication of temperature. So blue stars are hotter, red stars are colder. So at the bottom here, we see that the surface temperature for the blues are going to be, 30,000 Kelvin. The surface temperature for the reds are going to be only about 2,500 Kelvin. So we're seeing a difference of a factor of 100 there, difference. We can also look at the size. So we have things like supergiants, they're going to be obviously bigger. We can have giants, which are not quite as big. Mainline, or I keep trying to call them mainline, that was a thing back in Philly. Main sequence stars are kind of the average stars, and they go from, colder to hotter. The colder ones tend to be a little bit smaller. Our sun is right here in the middle. And then we can have dwarfs, which are smaller. So the dwarfs also, again, they all tend to be more similar in size, the dwarfs do, but they can go from cooler temperatures to hotter temperatures. This chart is showing us these horizontal lines are comparing to our sun, which is 1 solar diameter. So as we go down, we're getting to smaller than our sun. So this line here is 1/100th of our sun's diameter. As we go up, we're getting to bigger. So these supergiants are 1,000 times bigger than our sun. 1,000 times bigger than our sun, which is, massive. So you can imagine that some of these get very, very big. I mean, even these main sequence stars that are very hot main sequence stars are 10 times the size of our sun. Again, the color is going to indicate the temperature. So we're seeing very hot things versus very cold things. And we can actually basically, when we're looking at these stars, we can determine where they're at in their life sequence. So these main sequence stars are working their way through, they're kind of middle-aged. The supergiants are going to be older stars. The dwarfs are going to be older stars as well. Yes. The giants tend to be older stars. They've made it through their main sequence or their main life. They're about to hit the end of their time. So how do we know what sequence a star's at? How do we know what part of its life is a star at? So stars will birth in a nebula or molecular cloud. So, we're going to start off with this cloud of dust and gases. We're going to have gravity. We'll condense down into a protostar where we're having gravitational energy converted to thermal energy. It increases the temperature, and that's when we start to have nuclear fusion, that we start to turn into a true star. Same as I described with nebular theory. The star can then go into what's known as the main sequence. So this is where gas pressure will balance gravity and we will have a stabilized star. So it is hot enough to fuse hydrogen into helium. It will remain stable for most of its lifetime, so 10 billion years or so. It can then go into what's called a red giant. So that's where the hydrogen fuel is fully depleted and we no longer have thermal energy to counteract gravity, so it starts getting bigger. We're not, you know, keeping it in balance, so it'll start expanding. It will then have burnout and death depending on how much mass there was to start with. If there wasn't as much mass to start with, lower mass stars will become white dwarfs or planetary nebula. Higher mass stars will become neutron stars or black holes or supernovae. So if, I'll actually describe those different evolutions in a second here. Here we go. So they're all going to start out the same. They start off with this molecular cloud that we have cold gas and dust. We have a collapse of the cloud due to gravity, which will convert to thermal energy, and that will make our protostar. All right, this is where we can change. If we don't have a lot of mass in our star, it will move into the main sequence, but it will be smaller and red in color. And we will have hydrogen fusing in the core, but we never actually reach helium fusion, and we don't form a red giant, and those will eventually become a white dwarf. So basically we'll burn off all of the hydrogen and we'll only have the core left that will be the white dwarf. What our star is going to go through is that we will go from that protostar to the main sequence, and it's going to be a little bit brighter. It'll be yellow-white. It will have hydrogen fusing in the core. We will also fuse helium in our star. When it hits this hydrogen fuel is so depleted that we're not countering gravity, we will develop into a red giant. So basically we will get bigger. So if we go back to this, these giants, they are at that stage. They have burned through all of their hydrogen, these red giants. And so they would go into the red giant stage once we burn through all of the burn through all of the remaining fuel. It will turn into a planetary nebula. So it will, and then that planetary nebula will basically lead to the white dwarf, where we have completely run out of hydrogen fuel, and all that we have left is the core, which will slowly be cooling. If we have a lot of mass in that protostar, it will start off in the main sequence in the blue-white. It'll be very luminous and will have, again, hydrogen fusing in the core. When it runs out of enough, again, when the hydrogen fuel is so depleted that we can't counter gravity anymore, it will then become a supergiant instead of a red giant. This has a lot more energy. There's a lot more fuel here, and so it will become into a supernovae. These are where we're going to actually form a lot more of those elements, the higher elements. The supernovae, instead of becoming a white dwarf, can become either a neutron star or a black hole. All of these final stages are very dense materials. We are condensing things down into a small area, and there's a lot of matter still left in that area. So these are the densest materials in the universe. So after we've burnt out our star, we can either become that white dwarf, where we have the outer layers are all gone, leaving only the core. Here we are looking at an example of a white dwarf that would have a mass equal to our sun. It would be about the size of our Earth, so you can imagine just how dense this is. This next one over is a white dwarf that has 30% more mass than our sun, and it's much smaller than the Earth. So the more mass they have, the smaller they get, so the more dense they get. Neutron stars, which again are coming from the higher mass initial stars, are even more dense. So they're smaller and more massive than white dwarfs, so they're even more dense. They are very hot, but they have very low luminosity, so they're difficult to see. We can observe them, though, using sound. So pulsars are neutron stars that pulsate radio waves back to Earth, and we can actually record those. Black holes are also coming from the high mass stars. They are the densest objects in the universe. They only are going to come from neutron masses that are 3 times the mass of the sun, collapsing down. So 3 times the mass of the sun. These are only going to come from these, very large things that are then going through their in life. It is difficult to find black holes because gravity is so great nothing will escape them. Um, no light, no nothing. Nothing gets away from them. But what we can find are these typically giant companion stars that get trapped with the black hole. So that's typically how we identify the black hole, is by their companion stars. So our universe is everything there is. The universe has within it galaxies. Galaxies are collections of stars and other matter. The stars tend to be in solar systems. Um, Galaxies can be different shapes, so we can have spirals. So here we have an example of a spiral. This is the side view of a spiral. They can be elliptical, where they're a little bit more spread out. They can be irregular, where they don't have a nice pattern to them. They can also be dwarfs, where they're smaller than usual. We can have galaxies that will be clusters, so they can group up together. That's what we see here, is that it's just this amalgamation of a bunch of galaxies. So each of these dots is actually a galaxy, not an individual star or solar system even. So each of these, and this is this dot here, blown up to show us a cluster of galaxies that each has many, many solar systems within it, that each solar system has a star. We can also have superclusters, which are clusters of clusters. So basically, if we go from the smallest to the largest, you have a planet, which may have its own satellites. That planet will be in a solar system, which is orbiting, it's in a solar system, so it's orbiting a star. That solar system will be in a galaxy with many, many, many other solar systems. That galaxy might be in a cluster, so it might be in something like this. That cluster might be in a supercluster, and that will be in the universe. And the universe is made up of many, 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 many of these. So the universe is too vast for anyone to truly comprehend. It is massive upon massive. All right, changing gears a little bit, I will talk about material for the test and format of the test a little bit during actual week 3. But test taking 101. So what do you study? If you are given a study guide, study that. But don't just study the study guide. A study guide is to help you. It is not, okay, this is the only stuff you need to study. So my study guides are things that may or may not appear on the test, and it's not a comprehensive list of everything that's going to appear, because I want you to, the study guide can help you focus areas that you should concentrate more on, but don't only study the study guide. Did your instructor emphasize anything in lecture? That is something you should review. If a topic is covered multiple times, look over that. If the instructor seemed to spend a lot of time on a topic, look over that. If the instructor was extremely excited about a topic, that's something they probably like, so look over that. Have you seen the same thing in multiple lectures, quizzes, labs? That's probably important. For example, I've talked about nebular theory a couple times. That's probably important. I've mentioned the age of the universe a couple times. That's probably important. So if you see it over and over again, that's something to be looking at. Do you have your old labs, quizzes, exercises, etc.? Go over those. So look over your labs, look over your quizzes, look through your Pearson. These are the things that are going to help you in addition to your notes. If you have topics you find confusing, ask questions. That's what office hours are for. If you don't get something, don't just brush it off. Actually ask about it. Office hours are to help you. They are not designed for the instructor. They are designed for you. The instructor may use them to get stuff done, but they are designed as a time when the instructor is available to you as the student. I have office hours either before or after most of my classes. Those are really good times to talk to me because typically they're in the classroom. I do want to note that the 2 o'clock to 4:20 class on Tuesday, Thursday, and the 6 o'clock to 8:20 class on Monday, Wednesday, after those 2 classes, I have to get home pretty immediately. Actually, both the 2 to 4:20 classes, because I have that on Monday, Wednesday as well. So the one on Tuesday, Thursday, I can have a little bit more leeway, but the one on Monday, I am running home to feed my dogs between the two classes. So I need to get home in order to feed my dogs and, between 4:20 and 6, and also feed myself. So it's not a lot of time. And then the 8:20, getting out at 8:20, I need to get home and, let my dogs out and then go to bed because I am not a morning or night person. So those I'm probably going to be trying to get out the door a little bit faster. But most of the other classes, I either have office hours right afterwards, or, I'm willing to wait around a little bit. I also tend to be in there a little bit early, but before most classes, except the Tuesday, Thursday, 2 o'clock class, I have office hours right before. So I'm coming from my office down to the classroom. The office hours are posted on the syllabus, but really, office hours are to help you. If you have questions, that's a time to ask me. You can always email me too, but if you have questions, don't just try to figure it out on your own. How do you actually take a test? Take your time. I am giving you the entire time to take these tests. Your time period is 2 hours and 20 minutes. Take your time on your test. Seriously, you have time to read the questions quite carefully. You have time to read everything. Do read everything. There may be things hidden in the instructions. Do read the instructions. I have always wanted to give one of those tests that says, read all the instructions, and it gives you all these crazy instructions, and then the last instruction is, all right, write your name on the top of the test and turn it in. That you're not supposed to do anything. I've always wanted to do one of those tests. I haven't actually done it, but read the instructions. Don't just jump right into it. Exams may have non-bonus points for completing certain tasks. Do those things. If there's a point that says, I need you to write your name on this specific page, write your name on that specific page. That is a stupid thing to lose a point on. People often miss both of these. If you miss a point that is just, did you write your name on that page? You will feel ridiculous when you get that test back. Make sure you're actually answering the question asked. When I take a test, I suggest glancing through everything, read the instructions, but glance through everything so that you can kind of have an idea of what's going on with the test and then decide where you want to start. But when you actually are answering the question, make sure you're answering what's being asked. Sometimes if you're just throwing down random information, your random information may not be applicable, and sometimes you're throwing down wrong random information. So, did you actually answer the question? Was the question multi-part? Did it ask you to answer a compare and contrast? Typically, if you're comparing two things, you should talk about both things. If it's asking you to explain why on something, that means you need to have more than a 2-word answer. You need to give an explanation for something. So make sure you're actually answering the question asked and all parts of it. If you aren't going to be penalized for wrong answers, so typically you aren't penalized for something being wrong, like you're not going to get points taken away. The only time that really happens is standardized testing. So if the worst you can get is a 0 on something, write something down for every question. Do not leave blank answers. I have been known to give people points because they make me chuckle. They're a limited amount of points, but it's still points. I very rarely will give 0 on a short answer question if something is written down there, unless you have written something totally wrong. For example, if I ask you the age of the Earth and you tell me the age of the Earth is 2,000 years, that I wouldn't give you an answer or credit for. Or let me rephrase that. If I ask you when was the Earth formed, and you say 2,000 years ago, that I wouldn't give you an answer for, or give you credit for writing something down because it's just so off. But typically, if you write anything down, I will give you something. It may not be much, but it will be something, and something's better than nothing. Show your work on math problems. Let me say that again. Show your work on math problems. If I give you a math problem and you just write down a number, if that number is wrong, I can legitimately give you 0 on that. I tend not to do that. I tend to give you at least something if you give me the wrong answer. But if you give me the wrong answer and no work, I have no way of saying how close you were. So did you just type in your calculator wrong? Did you round it wrong somewhere? Were you using the completely wrong equation? So I can give you more partial credit if you show me your work so I can determine where you went wrong. Same thing on your labs also. Um, but showing your work is always better. But on a test, definitely show me your work. Review your answers afterwards. Don't just hand in your test. Go back and review your answers. Sometimes when you're reviewing your answers, you realize that, oh, wait, that's why that seemed familiar, that there's a similar question on another part of the test that may help you trigger an idea that you were kind of stumped on. So your test can actually help you. So reviewing your answers and don't just forget about a question after you answer it, kind of have it all in the back of your mind. So here's a hint. Look for answers elsewhere on the test. For example, if you forget the word Cretaceous and you are thinking about it, and you're like, I need to put this down. I have an idea of what this word is, but I can't remember exactly what it is. That very word may appear somewhere in another question. So it may be that as you're doing your multiple choice, that word is in the question somewhere. So maybe you've forgotten the term solar nebula and you need to use it in a short answer, but I have asked you a question as a multiple choice that's got solar nebula on it somewhere. That'll help you, one, with the spelling, and two, remembering the word. Here's an example of how you can use other questions to help you on a sample from an exam. So this part over here would be matching. And so here we have several questions and we have some of the answers are diamond, talc, and gypsum. These are all minerals. Here we have a fill in or a short answer, which is fill in the following minerals, and we have diamond. But we also see talc and we have gypsum. So the same three minerals that are in the matching now show up in this other question. Okay, this question is about hardness of minerals. So how hard are things? Well, this question is hardest natural material. Okay. Here we have soft mineral. Okay. And then we have number 1 on the Mohs hardness scale. So if we look at these, number 1 on the Mohs hardness scale, if we go back to this other question, here we have 1 through 10, number 1, and we see talc. Oh wait, talc is an answer. Well, maybe it's that one. Hardest material, natural material. Well, if 1 is here, 10 would be the opposite, right? And this is a blank, and diamond is one of our options here. Oh, look, diamond. And then this other one, gypsum, is on here, and we have soft material used in construction. That answer would be the gypsum. So if it's soft, it's going to be close to talc, which is also soft, and we have a blank spot here. So basically you could use these two questions in conjunction to figure out these things. I had people ask me, well, what order is 1 hard or soft, which is part of what the scale is, but they could also figure it out if they logicked out using these two questions that we had number 1 on here. Okay, we've got 1 is filled in. The hardest natural material is one of the options, and we had a blank for the other one, so 10 should be hard then. So you can use questions to help you answer other questions. So this is an example of basically, I gave you the answers on this. Did you notice I gave you the answers? The final thing I have to say is look over your test again. Seriously. This was something I said to my students last term. Seriously, most of you finished in less than an hour, some in 20 to 30 minutes. There were 30 matching and 30 multiple choice. That's less than a minute per question, or way less. Now, 30 matching and 30 multiple choice is just that part. There was also short answer. So if someone finished in 30 minutes, that meant that they, in 30 minutes, did 30 matching, 30 multiple choice, and then about 10 short answer questions in 30 minutes. I don't know how they did that. Surprisingly, they didn't do very well. So look over your test. Don't immediately turn it in. Actually do read through it at least once. And make sure you put your name on it. But take your time. It's not a race to see who gets done first. Okay, so now I'm going to go ahead and do the pre-lab video for week 3, which is looking at the stars and patterns in the solar, or not the stars, but patterns in the solar system.
Hello students, welcome back for another pre-lab video. This week in lab, we're taking a look at patterns in the solar system. The solar system is of course our neighborhood in the universe. It includes the sun and the planets. The prevailing scientific idea about how the solar system formed is illustrated here. A condensing nebula organized itself into basically a spinning disk with most of the stuff, the matter, at the center. That matter condensed and got so dense that it initiated nuclear fusion that made the star that we call the sun. But there was some stuff, a fraction of a percent of the matter, that was spinning around that star, and over time, gravity organized that matter into a lesser and lesser number of objects of greater and greater mass, and we know those as the planets, also asteroids, comets, things like that. The planets are not all the same, and that's sort of the point of this week's lab, is to look at some of the differences between them. You can see the Sun to scale over on the far right of this image, followed very closely by Mercury, Venus, Earth, and Mars. And then further out in the solar system, widely spaced and much, much larger, are planets like Jupiter, Saturn, Uranus, and Neptune. The distance between Jupiter and Saturn, Saturn and Uranus, Uranus and Neptune, is a very large distance, and these are very large planets, and that's very different from the relatively small planets that are closely packed in the immediate neighborhood of the Sun. To make sense of some of the patterns that we observe in the solar system, you're going to be provided a chart, and in this chart you're going to have various kinds of planetary data laid out for you. One of the first things you might pay attention to is how far away is a given planet from the Sun. You can measure that in miles, you can measure that in kilometers, or often astronomers simplify things by saying the distance of Earth to the Sun is 1 astronomical unit. So planets closer to the Sun than Earth, Mercury and Venus, have astronomical unit distances of less than 1 from the Sun. Any planet that's further away from the Sun than Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, they all have distances that are greater than 1 AU. Another variable that we'll look at is the period of revolution. This is how long it takes for that planet to go around the Sun. And you can see there for Earth, that's 365.25 days. So that's why we have 365 days in a year, except every 4 years, those 0.25s add up, and we have a leap year, which has 1 extra day in it. These are all calibrated for the Earth. So where Mercury, it says 88 days, that's 88 Earth days. And where Uranus, it says 84 years, that's not Uranus years, that's 1 Uranus year, and it's 84 Earth years. The speed at which a planet moves on its revolution is its orbital velocity. And that orbital velocity is shown in the last column here in both miles per second and kilometers per second. You might take a look at the data here for Earth. You can see that Earth is moving at 18.5 miles per second through space. So let's just go ahead and pause to appreciate that. Okay, here's 1 second. Great. So you just moved 18.5 miles through space in that 1 second. Pretty profound to think about that. You will notice that the orbital velocity is highest for the planets that have the lowest period of revolution, and it is slowest for the planets that have the largest period of revolution. So there's an inverse relationship there. That's the sort of thing we're talking about this week in lab, patterns. We can also take a look at the inclination of planets' orbits. Again, here we use the Earth as a reference, so you can see for the Earth it's 0 degrees and 0 minutes, but that is sort of an arbitrary distinction. So the idea there is the Earth orbits the Sun in a plane. That plane is called the ecliptic. The other numbers in this column are with reference to that ecliptic. So for instance, Mercury, you can see, is 7 degrees off from Earth's orbit around the Sun. And the other planets have less deviation from the ecliptic. Next up is the diameter of the planet, and you can see this listed here in both miles and kilometers. You will see that there's a very prominent breakdown here where the planets closest to the Sun, Mars, Earth, Venus, and Mercury, all have diameters that are in the thousands of miles, whereas the planets that are further away from the Sun, Jupiter, Saturn, Uranus, and Neptune, they all have diameters that are in the tens of thousands of miles. So this is a basic breakdown in the organization of our solar system. The inner planets, which are rocky, are called the terrestrial planets, and the outer planets, which are gaseous, are referred to as the Jovian planets, named after Jupiter. Next up, we have the relative mass of the planets, where Earth is 1. So this is, again, relative to the Earth. And you can see that, say, Mercury is much smaller than Earth and Jupiter is much larger than Earth. You can use the mass of the planet as well as the volume, which can be calculated from the diameter. And using those together, you can calculate the average density of the planet. So obviously, the planet's density is going to vary in terms of its subcomponents. So on Earth, for instance, the continental crust doesn't have the same density as the atmosphere, which doesn't have the same density as the core. This is the density overall for the entire planet. Again, here you can see there's a big breakdown where the terrestrial planets have densities that are much larger than 1, and the Jovian planets have densities that cluster around 1. So that reflects basic differences in their chemistry, which reflects basic differences in where they formed during the coalescence of the nebula that started off our solar system. We move on to polar flattening. This is basically a measure of how squished a planet is from its north pole to its south pole. In other words, how fat it is around the middle. And you can see that for the terrestrial planets, those values are relatively low. For the Jovian planets, they're relatively large. The number of known satellites shows a similar pattern. The Jovian planets tend to have a lot of satellites. The terrestrial planets tend to have relatively few. And then finally, we can take a look here at mean temperature. This is in degrees Celsius, but you can see that essentially the inner planets are hotter, the outer planets are colder, and the only planet that has a temperature between 0 and 100 degrees Celsius is Earth. That is the temperature that we need in order to have liquid water. Average temperature on Earth is 15 degrees Celsius. You're going to do an experiment looking at the distance of a little model planet represented by a can with a thermometer in it from a source of heat, in this case not the sun but a lamp, and you're going to put that can at different distances from that model sun, and you're going to record the temperature that results. You'll then compare this data with the pattern that we observe in the solar system and see if it matches up or if it doesn't. And if it doesn't, you're going to be asked to think about reasons why it might not match up, whether there might be other factors that we need to consider, such as a planet's internal heat production or the presence of greenhouse gases or other insulating variables. Thanks a lot for your attention. This has been Callan Bentley with another pre-lab video. Good luck this week in lab.
Okay, so I will explain in lab a little bit about how I have the experiment set up. Everyone doesn't have the setup, so there will be several setups that you will, each have a chance to do your experiments, but we'll have to kind of, when one's open, you can take your turn. But again, I'll talk about that during class, during lab, rather, in week 3. And I believe that is all. So thank you for your attention. In class, I will be doing this lecture. It will not take the entire time, so we'll have a chance for questions after the lecture. So I will see you in class.